Then there's advanced register notation. We're going to see how a lot of this is inheriting from the 32-bit architecture. Basically, the idea is that when you have a register, like let's just say RAX, just to take the first example, if you take the exact same register name but replace the R with E, for whatever reason E, that means that you're taking the rightmost 32 bits, half of the register, right? EAX is basically the right half of RAX. I think there's a picture in the, yeah, here. So if you imagine that RAX is 64 bits, which I guess, by the way, notice that this register is 64 bits because that is the amount of space needed to hold an address. But in any case, so if we imagine that RAX is this entire thing, then EAX is the right half of the exact same register. And then AX is the rightmost 16 bits. And in fact, you can address the high and low ends of, right, the high half and the low half of that, so that by doing so right here, you have only 8 bits, which is to say a single byte, which can be useful. Otherwise, I'm not sure that this table really is all that important, except I guess maybe except as it demonstrates the naming conventions. So for RBX and EBX, the same pattern applies, and you can see how to address those smaller bits again. And then so long as you have R over here, you have the corresponding E over here. And then for these things, which I don't think we're going to touch at all, well, let's just not even talk about. So here we see that each instruction consists of an opcode, which I think is basically like that 55 that we saw was the opcode for the push line of assembly. But then it has one or more operands. I guess actually, I guess that makes sense. One or more operands. So here, if we look at add, then add is the operation. And I guess we could even call that the opcode, although, maybe we could equivalently call its hex representation also the opcode. But in any case, it also has these two comma-separated operands. Each operand corresponds to a source or destination location. Sometimes it has just one, sometimes it has both. So for instance, just to talk this out, I think there are some versions of x86-64 that have it as the destination goes first and then the source comes next. But what we're going to look at, which is also a very common system, is that the source always comes first, right? If there's both a source and a destination, then the source comes first, the destination comes second. And so what this is essentially saying is take this value, whatever that is, as the source and add it into that destination so that effectively, the source register or whatever it is not affected, right? Its value is copied and then added into this so that, whatever was here, it is incremented or added to by whatever is over there. So anyway, the point is just that instructions tend to have either a source or a destination or both. And in this system, we use the pattern of always writing the source, then destination. So there are constant values. So in fact, we can now talk about this $OX. So dollar is indicating that this is actually a constant. X is indicating that it is hex code. And then 2 is the actual hex code. So since 2 is just hex for 2, then this is just the constant number 2. And so what this line is essentially doing is it's taking whatever is in, and remember, EAX was the return value register, and we are adding 2 into it, right? So whatever was in return, it now is increased by 2. Is essentially what this is doing. So now we've already kind of talked about how when you see a percent, we're talking about the address of a register. So in this case, where we talk about move source to base, what that effectively means is that the address of the source pointer, right? So whatever address is where you go to look up the source pointer, we make that the address of the base pointer. Why would you do that? Let's not worry about that right now. But just understand that that is effectively what this move command does, is it takes the thing in the source, takes a copy of it, and replaces it in the base. So this is taking the address of the source and using it to write over the address in the base, or the address of the base, I guess. There are also these things called memory forms, which are basically ways of, getting the value at an address. So for instance, if you merely write paren around your address, right? So parens around the address gets you the value at that address. But if you moreover put this like minus 0x4, then this is going to subtract 4 written in hex, but again, right, since 4 in hex is just 4, then that just translates very easily. So in any case, what this effectively does right here is it takes the address of RBP, reduces that by 4, and retrieves the value at that address, right? So basically, wherever the base pointer is, we go up, right? Because subtracting means we're getting smaller values, which we tend to diagram as being vertically up above. So we go up by 4 addresses and get whatever data is located there. That's what that is. So we take that data, and because we're calling move, then that means that we're taking whatever that data is and we're putting it into the return register, because EAX was the return register. Okay, so let's now imagine that the address at some moment, or like memory looks like this, right? So this address has this hex value, this address has this value, and so on, right? Just imagine that somehow a computer was like this. And we also just imagine that, again, somehow, let's not worry, I think, too much about how it got to this state, but that somehow the memory or the registers look like this, right? So you've got memory on the one hand, you've got the registers on the other hand. Remember, memory is in RAM, and the registers are on the CPU, so they're in different places. Let's note that in the following, as a bit of our own personal notation, I don't think this is any part of like any machine language or whatever, but just we will use the symbol m bracket x to mean look up the memory that is located at address x, right? So x is an address, and when we say m bracket x, we just mean look up x in memory. So you can see here that when we just have %RCX, we are just talking about the address, right? Notice that RCX up here in this table is a register, and its value is 4, meaning that essentially that is the address of that register. But now notice that if we take, for instance, parens around RAX, that is a memory lookup, right? That is saying take whatever RAX has, right, which in this case we imagine is an address, and look that address up in memory. So this, in a certain sort of way, this is kind of like going from the CPU to RAM. And so that's what this is, right? So this is memory. We are looking up memory with that command. Okay. This, because it starts with a $, is just the constant hex number 808, which, I mean, to compute that, just, not to get too bogged down in this, but you'd have to do 8 times 16 squared plus 0 times 16 plus 8 times 16 to the 0, right? So anyway, but the point is that I just want to emphasize that is a constant number, and it is written in hex. So in order to know which number it is, you have to think in hex. Now, if you did not have the $, it's worth noting that that number would cause a memory lookup for that hard-coded memory location, which you almost never want to do. There's pretty much no good reason to ever do that. But it is worth knowing that it can be done. If you tried to do it, it will do that. But, so just know that, like, with hard-coded memory locations, unless you have a really good reason for knowing the hard-coded memory location of some particular thing, you may not get what you expect. So usually you don't do that. Anyway, we'll come back to these, but I kind of want to skip to this one because I think it's nice to see the most general form of this. So parens generally mean that you are doing a memory lookup, as we've already seen. But what if you put 3 things into the parens, right? 1, 2, 3 things. What that translates into is that the first thing is the plus part, right? So if we do RAX, RDX, then that means RAX plus, then RDX times 8. So basically, I guess you could call this like an affine shift if you want to be like super mathy about your vocabulary here. But basically the idea is that it is a times and a plus. And then we do the memory lookup, right? Because it's all in parens, that means that whatever this comes out to, we look up the memory at that address. And you can run through the calculations, right? So if you take RAX, and we said that RAX is this 804, and you take RDX, where RDX is given to us as 1, then if you did 1 times 8, that's this part right here, 1 times 8, you get 8. And then if you did 804 plus 8, then you would get 80C in hex, right? Because 4 plus 8 is 12. The code in hex for 12 is C. No other digits are affected because there's no carry. So anyway, that's this most general form of a 3-place memory form. It has an equivalent form. You would get the same result as if you did this. Notice that in effect, basically what we're doing is we're just leaving the first thing blank, right? That comma right there has to be there to use the 3-place form. If you don't have that, right? If you don't put that comma there, then what you get is this. And it does not just treat the plus part as 0. Instead, it does a different operation, right? It does RAX plus RCX. So it's not as though the plus part were 0, but rather it just doesn't do the multiplication at all when you write it like this. And of course, yet again, outside of the parens, you can put a plus any number any number you want, and it is implicitly added onto the address, and then you do the memory lookup. And then, of course, if you do just a simple memory lookup and you write the 8 on the outside, then that just adds 8 to the memory and then does the lookup. So, okay, I think that's a decent discussion of how these forms are meant to go. I think there's some fairly sensible descriptions and constraints here, so we don't need to go through that. And I guess that's some useful information, but I'm not sure, like, it's just self-evident, I guess, once you read it. So anyway, okay, end of the video.